Okay, folks, is this on? We can get going. Thanks for coming. This is a class of 120 people, and there are 7 people in the room. I'm not exactly sure how to interpret that. My plan for today, since we got interrupted by the fire alarm last lecture, there's maybe just 10 minutes of stuff I wanted to button up with regard to the Bluetooth conversation. And then I wanted to move on to discuss a few more items of relevance for people's final projects. In particular, there are a bunch of people doing synths, and so I thought we would just take a moment to revisit some of the sound production content that we had touched upon earlier, but that might be a little bit rusty. And then I want to talk about some methods for doing attitude determination. So if you're interested in the 3D orientation of an object, figuring that out by way of some sensors that you may have attached to that object, I want to talk about that. And we'll see how much further we get beyond that. But let me start, unless there's any questions, I'm going to button up this conversation with regard to Bluetooth. I'll just very briefly remind you that at this point, what we've talked through is how BT Stack, this third-party library that the Raspberry Pi company ported, how this library allows for you to describe the database that you want for it to construct. It then compiles that database into a C character array that's properly formatted as Bluetooth attributes. And then we spent some time talking about how for those characteristics in that database that are labeled dynamic, I'll remind you that that label dynamic is us telling the compiler, I would like to handle the read and write callbacks for this characteristic, please. We talked about how we write the callback functions for those characteristics. The last piece of this that I just wanted to button up before we move on is the part of this whole process that we have not yet talked about is the mechanism by which a Bluetooth peripheral device, a GATT server, for instance, actually makes itself visible to a client that might want to connect to it and how that connection process occurs. And so we spent much of this conversation talking through in this, this hierarchy that I showed you a couple lectures ago. I'll just remind you up here at the top. There's this picture of sort of the whole Bluetooth stack. We spent much of this conversation talking through the generic attribute profile, GATT. That's where most of your development takes place. And we talked also through these packet handlers, which is how BT Stack in particular allows for your application code to interact with the rest of this stack. The last piece of this that we just have to discuss a little bit is another item here in the top of this stack, generic access profile. This is that mechanism by which devices make themselves visible to other devices and by which connection occurs. So let's just see here. Just some very quick background. This is the protocol that describes how devices discover and connect with one another. In a Bluetooth network, there are 4 possible roles that a device can assume according to this GAP profile, generic access profile. A device can be a broadcaster in which it just transmits data. It's just sending data out. It doesn't know if that data is received. It receives no acknowledgments about whether or not the data has been received. It's just broadcasting data. There are observers that just receive the data being broadcasted without acknowledging any receipt of that data. There are central devices that connect to peripheral devices by way of their advertising packets. This would be, for purposes of a lot of your final projects, probably like your phone. And then there are the peripheral devices. This is probably the role that the RP2040 is going to be playing in your final projects if you're using Bluetooth to make a Bluetooth server. These are devices that advertise themselves and then allow for central devices to connect to them. I'll just mention incidentally that, to my knowledge, I'm pretty sure that the Apple AirTags, that you can put on stuff and just kind of always knows where it is. I believe that happens by way of, I believe those are engineered to be Bluetooth broadcasters. So they're just sending out some information. The nearby iPhones and other Apple devices are observers that suck in those advertising packets. And they all have location information. And so from that information, you can figure out where that AirTag actually is. To my knowledge, that's approximately how that works. I don't think anything's actually connecting to the AirTag like a peripheral, at least not when they're just tracking it. In any case, I'll just mention, I've talked a few times about how at every layer of this protocol, there's a asymmetry. There's a more difficult role and a less difficult role, and that remains true here in the generic attribute profile layer of this stack. It is much easier for a peripheral device to generate advertisements than it is for a central device to scan for and then connect with one of those advertising peripheral devices. And we'll talk through the details of this, but I just wanted to point out that that asymmetry exists at this level as well. For our purposes, if you are making yourself a custom Bluetooth server device, one of your responsibilities is to construct a GAP advertising packet. This is the message that your device will send out into the world to advertise itself to other devices that may want to connect to it. Generally speaking, there are some things that you often find in this advertising packet, and then there are some sort of degrees of freedom that you could populate with whatever kind of information that you want. For instance, it's often the case in these advertising packets that you will broadcast your advertising type. Your advertising type, it's a 2-byte long piece of information. And what it advertises is the rules associated with connecting to you. You will almost certainly make yourself, what's the vocabulary that they use here? I think it's general discoverable. Essentially, this means you may connect to me, I will remain open to connection indefinitely. There are other devices that will advertise themselves as being, I think the vocabulary is limited discoverability, and that is to say, I'm available for connection, but I'm not going to be available for connection indefinitely. There's some time limit associated with this. That information in the advertising packet is handy for things like your cell phones. You may have had the experience of, if you've ever had a device where you push the button to connect to Bluetooth, generally speaking, when you push that button, it starts sending out these advertising packets, and it will advertise itself as being limited discoverable, which means you only have a certain amount of time to connect to me, and then I'm going to turn off to conserve battery or whatever. Your phone will often prioritize the limited discovery devices and put them at the top of your list. When you open up your Bluetooth menu for connections and you push that button, often it's the case that your headphones or whatever they may be show up at the top of the list. And that prioritization is possible because of this part of the advertising packet. It's saying, you better connect to me if you want to, because I'm going to turn off here in a second. And then you get to decide what else goes in this. You have 32 bytes to spend in one of these advertising packets. You can do some, you can allow for client devices to request a little bit more information, in which case you can actually pack 64 bytes, but generally speaking, you have 32 bytes to spend. Usually you spend a few of those on the advertising type, and then you can fill in the rest with kind of whatever you think might be useful or interesting to other devices. For instance, in this demo, I have part of the packet being the name of the device. So when we open up our Bluetooth menu on the phone, what we'll see here is Pico. And then this long UUID here is to indicate that the payload that follows it represents a 16-bit abbreviation for that big, long 128-bit custom UUID that describes the custom primary service that we had put together. So essentially what this advertising packet is saying is anyone can connect to me. I'm going to remain open to connection indefinitely. Here's my name. And if you do connect to me, here's the service that I offer. Here's the kind of service that I offer. It is also our responsibility to create a packet handler for this GAP connection process. There's some information here that I think I'm just going to scroll over, but in short, it looks something like the following. We write some packet handler. This is in some ways kind of similar to the read callback and write callback functions that we had put together, in that this kind of packet handler function is something that is described and specified in the BTStack documentation. We know the arguments with which this will be called. Those arguments include the packet type, the channel through which that packet arrived, and then the size of the packet and a pointer to a buffer where we'll store the packet. And then all that this state machine is doing is looking at the packet type and taking different actions based on sort of what's happening. When we first start up the system, BTStack will emit a packet of the type BTStack event state. It's in this state that we set up our advertising packet and start advertising. So for instance, we're setting up our the frequency with which we do our advertising. We set some parameters associated with that those advertisements, and then we call gap advertisements enable, which starts us just broadcasting these advertising packets. In any case, you can look through this documentation if you care to. That's just the last little piece of this that I wanted to fill in. And there's some configurations that you can make for this as well. So before we move on, I guess what I'll just summarize, I'll just make a few summarizing statements. So what we've spent the last 2 lectures talking through is how to put together a Bluetooth GATT server. That is to say, a device on which you have a database and a device to which a Bluetooth client can connect. Your phone, your laptop, another Pico if you cared to, whatever it may be. Your server only responds to requests from the connecting client. Those requests might include things like, tell me all the characteristics in your database. Or they might include things like, I would like to read that particular characteristic value, please. Or I would like to write that particular characteristic value, please. They may often be things like, could you please turn on notifications for that characteristic so that if you make any changes to it, just tell me about those changes. We are responsible for implementing the logic associated with responding to those client requests for all characteristics in our database that we have labeled as being dynamic. Dynamic means we are going to interact with that characteristic by way of our application code. And what we talked about is the way that we set up our application code for compatibility with this BTStack compiled database is that compiled database gave us a bunch of handy macros that described the handles of every one of these characteristics, their names or their addresses in that database, which is how the connecting client will refer to them. And we made a big struct that mirrored the structure of that database and connected all of the fields of our struct to the elements of that compiled database. What was convenient about this is what it meant that the values associated with these dynamic characteristics did not live in that database. Instead, they lived just in some global variable in our application code. And when we wanted to associate that variable with a particular characteristics value, we pointed the value field of that struct. The value field of that struct was a pointer, you'll remember. We assigned the value of that pointer to the address of that global variable. So what that means is we make modifications to that global variable, and in effect, what we are doing is changing the value of that characteristic in our GATT server. But that means because it's just a global variable, we can use that for other things in our application code. For instance, you might have a particular characteristic whose value represents the frequency of a DDS synthesizer. And your application code is just using that global variable to represent frequency, and it's computing DDS increments based on it and doing real-time synthesis of some sine wave or whatever it may be. But you've also associated it with the value field of this server so that if a client connects and changes that value, the frequency would respond automatically. If you care to, the demo video associated with this whole sort of example that I've been going through, it shows a whole bunch of examples of this. One of the fields of this example database represents frequency. You can change it from your phone and the sound changes in response. Another represents the color of a ball being drawn on the screen. There are a few that represent strings, character strings that are drawn onto the VGA screen, which you can update. You can write a new character string in and it updates there. And then there are others that are not writable but are only readable, that the Pico itself is just changing and making notifications, it's generating notifications that those values have changed, and you see them change on your phone. Any questions about this before we sort of close the book on Bluetooth things? Let me just mention, if you're interested in doing wireless communication between two Picos, two Pico Ws, your options include Bluetooth, like we've just discussed. You could make your Pico W a Bluetooth server, which is probably the role that it will play. You could also make it a client, and there's some examples here on how to do that. Bluetooth is not the only mechanism for wireless communication. You also have access to Wi-Fi, the Wi-Fi network through the Pico W. particularly through the CYW43 chip that's on it. And by way of that Wi-Fi network, you can send UDP packets, send and receive UDP packets to other Picos or to your computer or whatever it may be. And you can also send TCP/IP stuff. And that's a conversation that we're going to have, I think, next week. It occurs to me that we've been in the weeds here for a little while, and perhaps we'll take a step out of the weeds for the rest of this lecture and talk through some other stuff. Then we'll go back to some more detailed discussion of Pico-W communication methods. Let me just mention, by the way, another mechanism for wireless communication between two Picos that is oft overlooked is infrared. If you're trying to communicate between two Picos that aren't really that far away, right? So they're not like across campus from one another, but perhaps they are in the same room or a few meters apart. Maybe one is inside some sort of glass chamber in which an experiment is taking place, and the other is outside of it or something. Another mechanism for wireless communication is IR. We have in the lab, I may have to restock them, but generally speaking, I have a bunch of these really nice infrared receivers, these TSOP 34156 receivers. What makes these really interesting is they respond specifically to modulated infrared light of a very specific frequency. These, if I recall correctly, they're looking for 56 kilohertz modulated infrared light. So what that means is you could take this outside into sunlight where there's lots of IR, and they don't respond, they don't see it, so to speak. But if in that sunlight you also have an infrared LED that is blinking at 56 kilohertz, it sees that infrared LED. And so it means you can do IR communication even in environments that are noisy in the infrared part of the spectrum, because it's looking specifically for a particular rate of modulated infrared light. It's important, if you're going to use this in your project, read the data sheet associated with it, because it expects a modulation of a certain frequency. It also expects that that is sort of turned on and off at a specific rate. So it sort of goes brr, 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 where each of those fast brrs is at 56 kilohertz, right? And then for each burst, it will toggle. So, given those constraints for this particular device, what that actually lends itself really nicely to is UART serial through infrared. And this describes how you could set this up. So this is two microcontrollers sending and receiving to one another. To both of these microcontrollers, all that they think they are doing, all that your code thinks it's doing in this arrangement is serial communication. The code has no idea that there's anything infrared outside of here, and the code has no idea that there's any kind of infrared receiver here. All that we've configured in the software is a UART channel. What we have done is hooked up some infrared related components to that UART channel so that instead of wiring TX to RX and TX to RX directly, we've replaced those wires with this wireless infrared link. And I'll just summarize that the way that this works is the TX line of our UART line connects to the base of a BJT, so that when we do a UART serial transmission, which I will just remind you is just, pulling that TX line low and high for single bit times, right? When we do that, we're basically turning on and off, we're opening and closing a switch beneath that IR LED. That IR LED is being driven by a PWM output channel that is just configured to run persistently at 56 kilohertz, right? Exactly the frequency that this is looking for. And so the consequence is we do a UART transmission, and that BJT will turn on and off the 56 kilohertz modulated infrared light at exactly the right rate. And then on the other side, on the RX channel of this UART receive line, rather than plugging it directly into the TX line, all that we have here is one of these TSOP 34156 receivers, which is responding, toggling high and low in response to those bursts of IR. And to the input here, once you get to the input, if you scope that, it looks just exactly like UART. So it's handy for some applications It's because to your microcontroller, you don't have to do anything fancy. You're literally just doing UART serial. And all that you've done is added a few components here to make that a wireless communication link. It is, it works great over, meters to maybe 10 meters-ish or so. Like I said, because this is modulated, it'll even work in, if these lights happen to be putting out some IR, it'll work in this room. If you take it outside where the sun is providing some IR noise, it works out there as well. So it's handy to know about, depending what you're trying to do. I'll mention one gotcha with this. I learned something when I had a project that involved this, and the project itself was actually, it was for my wife who works at like an airplane museum, and she wanted a little thing that we could put on like a zip line. Looks like an airplane, slides on the zip line, and then you push a little button on a remote control. By the way, your TV remotes use this mechanism for communication, right? Push a little button on a remote control and it drops a quarter. And the idea was, try to get the quarter in a bucket. It was for like a kid's event. And I was working on it in my office, and every time I pulled my phone out, a quarter would drop. Turns out that on the iPhones, at least, it does the facial recognition. It's blasting IR, which is invisible to us, right? But it blasts IR a bunch to generate, presumably, a bunch of images of your face and to figure out if that's you. And it turns out that it is apparently doing so at the frequency that causes this to trip. And so I'd have this thing dangling from the ceiling and check a text message, and the quarter would drop. Like, well, what the hell's going on? So you got to be careful with that kind of thing, I suppose. Could be a feature. Yeah, Bruce? It's also very legally simple. You don't have to worry, generally speaking, about breaking laws if you're doing infrared communication, which is a nice feature of a communication method, right? Any questions about this? Okay, so then another topic I wanted to just bring up / remind you of is there's a number of groups that are doing various varieties of sound synthesis projects. So there's a few conversations that we can have with regard to sound synthesis. There are projects taking place that involve making a synthesizer, and some of those synthesizers are trying to emulate actual real instruments. They're trying to make the Pico make a sound that sounds like a guitar or a violin or a drum or whatever it may be. So that's a conversation to have. There are other groups that are making bizarre synthesizers that just make weird noises. And so we can have a conversation about how does one make a device where you can play and make strange, sort of unpredictable noises. We'll have that conversation as well. And then there's a separate group of projects that are making things like video games for which it would be nice to have background music. And I'd like to have just a brief conversation about how one might set up background music in a way that doesn't take a bunch of CPU time. You may remember this from our DMA lecture. It involves using DMA channels, but I think it's worth reminding you about. But let me start with the first of those. So let's suppose that you are interested in, I'm going to go to one of Bruce's pages here. Let's suppose that you are interested in, I had it linked up here, hold on. I know there's an RP2041, but I'll start on this one. Let's suppose that you're interested in trying to emulate the sound of a musical instrument, an actual musical instrument that people recognize the sound of. And you want to make this thing sound like that thing. You essentially have three options. One of those options is you can do additive synthesis. What additive synthesis involves is you take the instrument that you are interested in emulating, and you do a frequency analysis of the sound that that instrument makes. So another way of putting that is you play the instrument or you play a recording of that instrument, and you generate a real-time FFT or spectrogram that shows you the frequency content of the sound that that thing makes over time. And then the strategy is you look at that frequency content and you ask yourself, what are the loudest frequencies, the frequencies in this spectrum with the most power that are apparent coming from this particular instrument? There's some instruments, I'll just mention incidentally, that have really obvious power at really obvious frequencies. Stringed instruments, by and large, have this property because they have such predictable harmonics. If you look at the spectrogram, for instance, of a violin, what you will observe is fundamental and then just a beautifully stacked set of harmonics. Now, if you're interested in emulating a violin, I'm actually going to advocate for a different of these strategies. But it's just to say that for some instruments, this is relatively simple. The frequencies at which there are power are obvious. For some, it's more subtle. But the general strategy is you observe which frequencies have power in them, what is the relative amount of power at each of those frequencies. 100 hertz is 2 times as loud as 200 hertz, or whatever it may be. And then you make a separate DDS synthesizer at each of those frequencies where you observe noise, you observe power from the instrument that you're emulating, and you set the amplitude of that particular DDS synthesizer according to the power that you observe in the spectrum of the actual instrument. It's very simple in principle. In practice, this can sometimes be a little bit tricky. I can show you an example of this, which I can't remember if I've shown you before. If I have, that's okay. So for example, and an example instrument where this is a little bit challenging is a bell. One moment, past MNG projects. I think I did show you this already, but that's okay. Let's see. Oh, it's here somewhere. Where is it? Bell. Here it is. So what this student did was additive synthesis of a bell that is absent from the tower. Aiden knows which one it is. I don't know. C sharp. Okay. He wanted C sharp. And so the way that he went about this is he went up into he was also a chimes master, went up and recorded a real bell. That's an actual bell from the Cornell Bell Tower. He looked at the frequency content of that and observed what are the frequencies present in the sound of that particular bell. But it's more complicated than that, as it turns out, for bells, because when you first strike the bell, you'll observe a certain amount of power at certain frequencies. And then as the bell rings, the power attenuates from the different frequencies at different rates. And so getting this to sound right involves not only identifying what are the frequencies at which there is power present from this bell, but also what are the functions, the individual functions for each of these frequencies that describes the rate at which they decay. He had to get both of these things right, and I think I've played this for you before, but pretty darn good. So what we just listened to, that synthesized bell, was synthesized by way of this first strategy that I'm discussing, which is additive synthesis. That is just a collection of pure sine waves. I can't remember exactly how many. I think it's on the order of 30. Do you remember, Bruce? I don't remember. Something like that. Yeah, something like that. So it's not a tremendously large amount. You would have no problem fitting that many onto the RP2040, right? And you can make really, really nice sounds. I'm just cautioning you that sometimes this is relatively easy. In the case of the bell, this was a well-scoped MEng project. In order to get that sound, that was a well-scoped project for 2 semesters worth of work, because the bell is a challenging instrument to get this right for. But there are instruments for which this is much simpler. I will mention too, just as an aside, a version of additive synthesis that's really interesting and that Bruce spoke to a little bit in the lecture that he gave is you can do additive synthesis of a human voice. This is a speech vocoder, okay? And the way that this works is you, just like the bell, you generate a collection of DDS synthesizers that are generating just pure sine waves. You also, let's see, I'm just going to draw a silly picture. So you're taking in a bunch of microphone data, and you're passing that microphone data through a collection of overlapping bandpass filters. So audio data comes in, raw audio data comes in. That data is going through this bandpass filter, this bandpass filter, this bandpass filter, this bandpass filter, a bunch of them, right? Probably more than 8. And coming out of each of these bandpass filters is a filtered version of that person's voice that has only allowed, it only allows the components of the person's voice in this frequency range to pass through. You do that for another frequency range and another frequency range and another frequency range. Take the outputs of all of these filters and you figure out how much power is coming out of each of these. What is sort of the average amplitude coming out of each of these filters? And associated with each filter, there's a pure sine wave synthesizer at the frequency that centers at this filter. You use the power coming out of this filter to set the amplitude of the associated sine wave. You add them all up and send them out to a speaker, and what comes out is understandable voice. It's not your voice anymore. You have stripped it of all identifying information. It is a purely robotic voice, but it's understandable. And it takes shockingly few of these frequencies to make something that is in fact understandable. It's really neat. There's another strategy, just by the way, which is rather than generating pure sine waves associated with each of these filters, another strategy that can be deployed is you have a buzz generator, a noise, just like a whole bunch of frequencies at once. You take that spread spectrum buzzing sound and you send that back out through these filters with the power coming out associated with, mapped to the power coming in through each of these filters. And what comes out there also is understandable voice. Bruce? But it sounds like a whisper, yeah. This has been on my mind recently because, has anybody seen the 2010 remake of Tron with Jeff Bridges? I watched this last week and I hadn't seen it in like a decade. You may be aware that that movie has a famously fabulous soundtrack by the electronic band Daft Punk. And so it's got me on a Daft Punk kick. So I've been re-listening to a bunch of Daft Punk. In particular, their 2013 Random Access Memories, which uses a vocoder in like every song. So wouldn't it be neat if you are doing a vocoder, wouldn't it be neat to try to emulate that vocoder, and then for your final project you could do, or for your final demo rather, you could do karaoke, where you take the role of the Daft Punk part of the song, you play the vocoder, and you pitch it appropriately just like the song does. That one's tricky because I can hear the S's and the T's in that vocoder. I don't know exactly how they're getting such nice S's and T's, honestly. I don't know. How would you go about this? My inclination would be to take that first part of the song where it's largely a solo by the vocoder, I think, and I would do a frequency analysis of that voice to see if we could identify whether that voice is composed of some number of distinct frequencies. And then that would inform, I think, the number of bandpass filters that I chose to try to emulate that voice, I think. And then I think I'd start playing with it. I would try by just using pure sine waves and see how that sounded. I'd try maybe introducing a little bit of noise as well. Perhaps that's how they're getting the nice S's and T's, is by introducing some buzz as well to the output filters. I'm just not sure. It'd be really neat though. Yes. So what Bruce is pointing out here is, I mentioned another strategy is for you send a buzz back out through the filters. It needn't necessarily be a buzz. You could send a guitar synth back out through the filters, and what would come out is something that sounds kind of understandable, but it sounds like a guitar is speaking. If you poke around online, you'll find examples of this. People have done this with like pianos, where they make a piano kind of talk, and you do that largely by way of the strategy that I'm describing. Okay. So that's all to say, if you are interested in emulating an instrument, or in fact emulating a voice, you can do that by way of additive synthesis. I mentioned that there are two other strategies. Another strategy is FM synthesis. FM synthesis is very different. It involves two DDS synthesizers of two different rates that you sort of convolve with one another. So you have one synthesizer that's producing your output waveform. You have a second synthesizer. You can see, it's hard for me to point to, but the other synthesizer is being used to modulate the frequency of the second synthesizer. So in effect, rather than having your DDS synth produce a pure sine wave, you're using a second synthesizer to modulate the frequency of the sine wave that's being output, so it dithers. And there are knobs here that you can turn that describe things like, you know, by how much does the frequency get dithered? At what rate does it wiggle back and forth? What are the relative amplitudes of these two sine waves? What are the relative attack and decay rates of these two things? So in effect, what you're constructing is a search space of sounds to which you could, if you cared to, on a synth, tie like actual physical knobs, right? So you could have an actual physical knob associated with the frequency of the modulating DDS wave, for instance. And as you turn that knob, the sounds that come out are unusual. And what's sort of interesting about this, let's see. So you can poke around in this space. I think Bruce may have showed you that in his lecture as well. So that sounds an awful lot like a plucked string. It has actually nothing really to do physically with a plucked string. What we've done here is explored this search space of possible sounds and found a place in that landscape that sounds kind of string-like. And so you say, okay, I'm going to set the parameters to that, and that's pretty much a string synth. But then you can explore this search space and you'll find other places that sound kind of drum-like. Kind of a weird synthy drum, but drum-like. And you can explore other parts of this search space that produce sounds that are just bizarre, right? And so the first approach that we talked about was a very sort of, you focus your energy on trying to produce, to the greatest extent that you can, to try to emulate the frequency content of the instrument that you want. This is a wholly different approach where you say, I'm going to engineer a search space, and then I'm going to explore it until I find a place that sounds kind of like what I'm looking for. For any of these projects that are making weird synths, making weird sounds, this is a nice approach because you can just put some knobs on this and sit there and explore forever these different sounds that this thing can produce. And then actually, hold on, Bruce, I'm going to pull up your actual RP2040 version of this. Bruce has RP2040 examples of all these things, which he did show you in his lecture, but it occurs to me it's probably a nice idea to just remind you of this. So here on the RP2040 page, there exists an FM synth demo from which you could get started. And then also, I talked about this other version of the third option that you have for emulating instruments being physical synthesis. Karplus Strong is an example of a physical synthesis algorithm. What this is doing is, in a very clever fashion, you are actually solving the wave equation and producing the sounds that the wave equation actually produces. So this is a nice way to generate stringed instrument sounds, guitars, violins, and so forth. And what Bruce is showing here is the spectrum associated with one of these synths. And I mentioned earlier that for many of these stringed instruments, you get beautifully stacked harmonics. You can see that here, right? This looks like it's playing a scale. Any questions about this stuff? Okay. Something else I wanted to point you to is there are a few groups that are doing projects that require knowledge of the 3D orientation of something in space, your head or a golf club or something. And if you want, this is a different problem from the problem that we did in lab 3. In lab 3, we were determining the orientation of that arm, right? And we did that by way of only an accelerometer and a gyroscope. If you're interested in full 3-axis attitude determination, you require, I don't know if I linked this web page up. I didn't, hold on. You require at least 2 vectors in order to do this. Rigid body. And there's a strategy here for doing this that I want to speak to for just a moment. So as with everything, attitude determination is, again, a whole field of study. There's a gajillion techniques for doing attitude determination in more or less sophisticated ways. Each technique has its own set of advantages and disadvantages. The simplest, arguably I suppose, the simplest way to do attitude determination is what's called the triad method. Triad stands for triaxial attitude determination. What you do here, let me just state that if you're trying to solve the attitude determination problem, another way of rephrasing that is what you're interested in is you want the rotation matrix, the direction cosine matrix, that rotates you from some standard frame that you want to know the orientation of your thing in. You know, maybe it's this frame. I'm interested in knowing orientation relative to me. You want the rotation matrix from that frame to a different frame of reference, which is the frame of reference of the rotated body. We can do this. Well, let's suppose that we have 3 vectors, okay? So in order to do this, you need to have knowledge of at least 2 inertial vectors in both frames of reference. Here on Earth and in the lab, and probably for most of your projects, those vectors will probably be gravity. In this frame, we know which direction gravity points. And if we have an accelerometer on our device and it's not accelerating too much, right, then that accelerometer will read the direction of gravity to be in some other direction because it's facing in some weird orientation, right? But that's the same vector. And so we can talk about that vector from our frame that we are interested in, and we also can measure the direction of that vector in this rotated frame that we're trying to figure out how to rotate into. So probably in the lab, many of you will use gravity as one of your inertial reference vectors. Probably in the lab, the other inertial vector that many of you will use if you're trying to do this is north, magnetic north. You can get a magnetometer and put it on your device, and now you know in both this frame and in the rotated frame, north and down, basically. And from that, we can solve the full attitude determination problem that I'm going to talk about here in a moment. Let me just mention, if you're doing this, it's pretty hard to get magnetic north in the lab. That is a noisy place, the lab. So if you really want to solve this problem, what you might consider doing is get a big old permanent magnet and stick it nearby, close enough that it overwhelms Earth's magnetic field, and use the direction to that magnet as your north, right? And so then your 2 vectors would be gravity, down, and the direction to this magnet that you have nearby, which would be playing the role of north for you. Okay. But let's suppose that you have these 2 vectors. Well, I'm using the little superscripts n and b here to represent inertial frame with the n and body frame, the orientation of the body. And what we're interested here is this rotation matrix Q. There does exist some rotation matrix that when it acts upon each of these vectors in the body's frame, rotates that vector into the inertial frame. So let's suppose we had 3. Gravity, north, and I don't know, direction to the sun, or something like that. If we had these 3 vectors, we could organize those 3 vectors into a matrix, a 3x3 matrix, and summarize those 3 equations into a single vector equation. This matrix of our vectors in our inertial frame is equal to those same vectors represented in our body frame acted upon by some rotation matrix Q that we want to solve for. Well, with 3 vectors, you can just solve for this, right? So all that we do is we invert the matrix composed of these vectors, multiply this collection of vectors by the rotated ones, and the consequence is that we have solved directly for that rotation matrix. Now, if you only have two vectors, you cheat a little bit, where you say, here's going to be my first vector. Maybe this is down for you, okay? My second vector in my organization here of body frame vectors is going to be my first measured vector, down, crossed with some other inertial vector, magnetic north. That's guaranteed to be orthogonal to that. And then our third vector is our first one crossed with the cross product of the previous two, which makes it orthogonal to both the first and the second. So this is an orthogonal set of vectors composed from only two measured vectors in the inertial frame. And we deploy the same trick and solve directly for the rotation matrix here. So with an accelerometer and a magnetometer, which tells you down and it tells you north, you can solve for the full orientation of any body. You can't do this with one vector for perhaps the obvious reason that you can spin around it and there's ambiguity. Any questions about that? What if you were in space? What if you had to solve the attitude determination problem in space? Your accelerometer doesn't get you much anymore. What vectors do you think are often used by spacecraft in order to solve this attitude determination problem? Any thoughts? Well, the answer kind of depends where you are. If you're in Earth orbit, you do still have access to the Earth's magnetic field. And so you can use a magnetometer. Other common vector measurements for solving this problem might include a sun sensor. So a sensor that just tells you the direction of the arrow that points to the sun. And so rather than using down and north in Earth orbit, it may be the case that you instead use north and direction to sun. We know both of those vectors as well in both the rotated spacecraft frame and the inertial frame. Granted, the sun moves, right? And so we have to update that. We have to also know time, okay? But that's an answer. But what if you're in deep space? How do you do it then? You're in the cold void between planets. No magnetic field really to speak of. Nothing. What do you look at? The stars. You look at the stars. And so essentially every spacecraft that can afford it really does its attitude determination by way of a star tracker. A star tracker is a camera that looks at the field of stars. It has an onboard star catalog so that it can correlate what it sees against its catalog and figure out the rotation that takes that catalog to what it sees. So it massively overdetermines this problem because rather than just using two vectors, down and north or north and sun, it uses as many stars as it can see, which means these star trackers, they will tell you the attitude of your spacecraft, to just truly exquisite precision. Here's a really big one. Fractions of fractions of fractions of degrees. And it's because it so massively overdetermines the system. And because those vectors are so, they don't change, right? The stars are so far away that that's a really well-known field. And so it allows you to solve this problem really, really well. Now, if you're, traveling relativistically or so far that the star field changes, then it's a different game. Then what would you look at? I don't know, quasars? I don't know. In any case, that's all we have time for today. So next week, what I'd love to talk about, I want to talk about Wi-Fi communication, TCP, UDP, and so forth. I'd like to talk a little bit about the boot sequence of this thing. What's everything that happens before main gets called? There is some stuff that happens before main gets called. I want to have that conversation so that we can have a subsequent conversation about writing your own custom bootloader, which is just a fun conversation to have. And then more stuff after that. But in any case, I'll see many of you this afternoon. I'll see the rest of you on Monday.